Hello. This lecture provides a brief summary of the process that's used for the production of steel. This is probably a review of material that you learned in your materials of construction class, but just to make sure that we're all on the same page to start off with, I thought I would put this together. So it just gives an idea of the method that's used for producing structural steel. The production of structural steel is broken down into three primary steps. The first step is the production of pig iron, and this is where you take raw iron ore and coke and some other elements, and you purify the iron to make pig iron, cast iron, or wrought iron. Pig iron is the most useful for us in the context of steel, but iron by itself is not appropriate as an engineering material. It doesn't have the ductility that we need for an engineering material, and it is susceptible to fracture. The second step is to produce raw steel. So raw steel is made up of about 96, 97% iron, but there are alloying elements in it that give it the properties that we really rely on, like the extra strength and the ability to resist abrasion, the ability to resist fracture. So the pig iron is combined with alloying elements in an open hearth furnace or a basic oxygen furnace or an electric arc furnace, an EAF or a BOF. And after the heat of steel, after that batch of steel is complete, after it has all the chemicals in it that is needed, then one of two things happens. It's either cast into ingots and then set aside so it could be worked later into the finished product, or it's sent to a continuous casting operation where it is manipulated into its finished products. So then that brings up the third step, which is the the roughing and finishing process for the steel, and this is where the steel is rolled into its final product. So the shapes that we're looking for are plates, bars, pipes, rods, W shapes, angles, channels, and things of that nature. So these are the basic three steps. Production of pig iron from raw materials, the production of steel using iron as the basic constituent with some alloying elements, and then the roughing and finishing process. Okay, this is an image that I borrowed out of a textbook so long ago that I don't remember which one it is. So I apologize, I don't have a reference for it. But we have the iron ore, the limestone, and the coal that are going into the blast furnace. So limestone and iron ore together form sinter. And then the coal is baked in a coke oven so that you get coke, which burns hotter than coal does. So then this all goes into a blast furnace, and you can see these are bottle cars at the bottom where the molten iron exits the blast furnace and goes on to the next step in the operation. That might be directly going into a basic oxygen furnace. That might be going into some ingot facilities or something like that. Basically, you combine the molten iron with lime and other fluxing agents, and maybe with some scrap metal as well, and you get from the iron step in the process to the steel step in the process. And then after you have all of the chemistry right in the heat or the batch of steel, then it goes into a continuous caster or into some type of a roughing and finishing operation. Okay, this image conveys to a large extent, the same information that was on the previous slide, except this comes out of a Nippon Steel catalog instead. Again, you have the raw materials going into a sintering plant, iron ore and limestone. The process of sintering is basically taking powdered material or pulverized material and making granular material out of it. So it comes out like a gravel, as I understand it. I've never actually seen it firsthand, but that's my understanding. Okay, coal goes into a coke plant. The coal is basically baked down to a product that is called coke that burns hotter than coal does. These are fed into a blast furnace, and out comes pig iron. The pig iron goes into a basic oxygen furnace where it's combined with alloying elements, and then it goes into a continuous caster and results in rough sections like a slab or a bloom. This is a picture of a blast furnace in Belgium, as I understand it. And The web page is cited here is a German web page, and this guy likes industrial photography. So if you have a few minutes, navigate to that web page and take a look at some of his pictures. If you have any interest in photography, and then it's pretty interesting. And if you have any interest in steel, there's a lot of steel mills and things like that that he's taking photos of. But basically, you can spot these blast furnaces because they tend to be very tall operations. They're a rather large structure. There's a blast furnace in Middletown for what used to be AK Steel. So if you drive by on 75, if it's a clear day, you can look off to the west of the highway and see the blast furnace. This is a bottle car that's on a rail line. So basically the pig iron is being tapped from the bottom of the blast furnace and is flowing down into this bottle car, and then the pig iron will be transported to a different part of this steelmaking facility. It'll either be cast into ingots or it'll be dumped into a basic oxygen furnace and combined with other elements to form steel. This is a basic oxygen furnace, and you can tell the difference between this and a blast furnace because a basic oxygen furnace isn't nearly as tall as a blast furnace is. So basically, this is just a big container, like a pot, if you will, called a tundish, and they use this to mix the pig iron with the alloying elements to form the steel. Okay, after you have the steel batched, one of two things happens. This molten steel is either molded into ingots or it's fed into a continuous caster to form and then formed into rough shapes such as billets, blooms, and near net sections. So the two are different operations. Basically, if you want to form the molten steel into ingots, it's called teaming ingots. Then basically you're setting that steel aside so that it can be reheated later and then shaped into the finished products. The alternative is to take the molten steel and put it into a continuous caster right away before it cools and solidifies, and then the steel is formed into its rough shapes right away. So teaming ingots is probably an older process. Basically, you have these molds that are filled with the molten steel. The steel is allowed to cool and harden, and then when they want to form that steel into a rolled shape or into a plate or something like that, they have to reheat the ingots back up to a high temperature, and that reheating process takes a lot of energy, so it's not as economical as continuous casting is. When they reheat these ingots, they put them in an oven that's called a soaking pit and let them soak until they get to the temperature that's needed. Okay, this is an image out of an old materials textbook, and I can't remember the author and the title. Actually, I think the book's in my office on campus, so I apologize for not having a reference there. But basically, these are molds that would be filled like the bottle car was from the basic oxygen furnace, and then you would have big blocks of steel that could be shaped later on. And you might set these ingots aside for a period of weeks or months or possibly even years before the steel is shaped into its finished product. These things are very heavy, so you often see these rail lines on steel yards that are devoted just to moving raw materials around, like ingots and things of that nature. Okay, this shows the process of teaming ingots, or basically molding the molten steel into ingots. And if you look at the bottom of this slide, you can see the ingots passing below this tundish, and the tundish is being tipped up, and the molten steel is about ready to be poured in. So this area down here, these are the ingots that are passing below the tundish. There's probably a rail line down there, and this itself is the tundish that's being emptied into the ingots. Then back here, you can see another tundish in the background being charged again with another batch of pig iron, setting up the next heat of steel. So after the molten steel has solidified, then the steel is removed from the ingots, and that's called stripping the ingots. So you can see the mold here has been flipped upside down. The steel is being removed from the ingot, and then you can see over here on the right are some ingots that are placed on this rail car to go into storage, and then the ingot molds are placed in this rail car over here on the left to be reused for the next batch of steel. So if you look carefully down in this region here, you can see that this steel is still red hot, but it has solidified. So the image on this slide shows the third step in the process, and that is the roughing and finishing of steel. So the first step is to make sure that the steel itself is at a temperature that's appropriate for final rolling. That temperature has to be hot enough so that the steel is pliable, but it can't be so hot as to make the steel liquid. So a temperature of around 2350 to 2400 degrees Fahrenheit is what you're looking for. And then the steel goes through a series of rolling stands until it ends up as its finished product. Then the steel is still hot, so it goes on to a cooling bed. And then after the steel is cooled down roughly to room temperature, it has to be straightened so that it's not warped or curved. And then you end up with the final product. So this photo shows an ingot that was reheated after it was cooled. So you took iron from a blast furnace, combined it with alloying elements to form steel. The steel was dumped into an ingot mold to form an ingot that was allowed to solidify. Then the ingot was stripped from the mold and stored. Then they decided they wanted to use that steel and make some W shapes or some I-beams or channels or something. So they put that ingot into a furnace called a soaking pit. And then after the ingot is reheated to a temperature around 2300 or 2400 degrees Fahrenheit, then it can be worked and shaped into its finished product. So this is an ingot being removed from a soaking pit. Okay, the rough sections that we deal with are shown here. So we have blooms, billets, we have slabs, and near net sections. So a bloom is basically a square section that's roughly 6 by 6 or 12 by 12 in cross section. And these are generally rolled into structural shapes or structural sections. Billets are also square in section, but are smaller than blooms, and billets are generally rolled into smaller products like bars or wires. A slab is something that's usually rolled into a structural plate or sheet steel, and slabs are generally 6 to 9 inches thick and 24 to 60 inches wide. And then a near net section is not rectangular, it's not square. It has a shape that is approximately like an I shape or an H shape. And the idea is that these are produced as a rough section, but they're closer to the final shape so that there's less energy needed to get from the rough section to the finished section. I have pictures coming up and a few slides that show what a near net section looks like. So this slide shows billets on the left, shows slabs there in the center, and then blooms on the right. So the billet steel would be rolled into like bars and wires and things of that nature. The blooms would be rolled into structural shapes like channels or I-beams, and then the slabs would be rolled into plates. So this shows a picture of a blooming mill. So you can see that ingots have come out of the soaking pit. They're shaped like an ingot, just a big block of steel, and they need to get into the shape of a bloom before they can be rolled into a plate. So this is a big mill that has a series of presses that shape that rough ingot into the shape of a bloom, and then it goes into the final rolling stands. Okay, so this image from worldsteel.org, an interesting website if you're so inclined to check it out, shows billets coming off the roughing mill, and they are still red hot, but they are solidified. This shows a slab on a roughing mill that's being cut to length. You can see the torches there in the background that are cutting this slab to length. So the next step would be to put this through a series of rolling stands where you're going to decrease the thickness and you're going to increase the width and the length of this product. All right, now the alternative to casting or teaming ingots, letting them solidify and then reheating them before they're finished, is to go directly from the molten steel into a continuous caster so that you don't have to expend the energy to reheat the steel. So this picture here shows a continuous casting operation where molten steel comes in from the top of this machine or this process and comes out through the bottom, solidified into what looks like either a bloom or a billet. This is another view of the same continuous casting operation. And basically, as the steel flows from the furnace, it's poured into a tundish and then poured into the top of this continuous caster. And as it flows down through the continuous casting operation or through the caster, the steel flows through water-cooled forms or molds and forms a solidified shape. So it looks like here we have blooms that are coming out of this particular continuous caster. So they're still bright yellow. They're very hot, just below the melting point of the steel. Still very pliable, but they are a solid at this point. Now, this slide shows rough sections coming off of a continuous casting operation, and these rough sections are near net sections. So if you look at the cross section of these pieces, the ones on the left anyways, they look like H's or I's. So the idea is that rather than starting with a rectangular cross section and shaping that into an I-shaped section, an I-beam, for example, then you can start off with something that's closer, and it basically takes less energy, less time, and less maintenance on the machines and things of that nature. So this is a near net section, which is an alternative to a bloom. Okay, it looks like back here in the back part of this, though, it looks like they do actually have some billets or blooms that are back here as well, but these are near net sections here in the front. Okay, now the process of finishing starts with a rolling operation. And the basic idea is that you go through a series of rollers that are the inverse of the shape that you finally want. So you start off with roughing in a breakdown mill, then you go to an edging mill, and then you go to a finishing mill. And by rolling back and forth through a series of big rolling mills, then you get from the rough section into your finished section. So these slides here to the right of center show the process. You start off with a slab or a bloom. It goes into a roughing operation where it's a rough H shape, and then finally it comes out looking like an I-beam or an H-beam. Okay, and this is an example of a rolling mill. Lots of pressure is applied here. So at the top of this machine, you can see hydraulic actuators or hydraulic cylinders that are used to apply their pressure. The steel at this point is very, very hot so that it's pliable. And then you can see the water-cooled rollers down here. The rollers are made out of steel. They can't get too hot or else they become damaged, so they're cooled by water. Okay, and if you look at some of the videos that are posted onto the Canvas site for this, you can see this operation as a video instead of just as a still photo. Basically, the steel passes back and forth through this process, and a rough section that might have been 12 or 16 feet at the beginning actually gets quite long. It could end up being up to 100 feet long as the steel gets reshaped. Okay, a couple of different views of different rolling operations. You can see the rollers that are shaping the steel, both in the image on the left and on the image and in the image on the right. Okay, after the steel is rolled to its final dimensions, then it has to cool back down to room temperature. So they go and they sit on a cooling bed, just a part of the steel mill where they're allowed to cool from the finishing temperature, 2350 to 2400 degrees Fahrenheit, back down to room temperature. So the shape on the left, you can see that it's still red hot, and over there on the right, you can see the ends of the members. See how it's kind of squished out at the ends. These haven't been cut to length yet, so it kind of gives you an idea of how the material goes from a 12 or 16-foot long bloom or near net section and ends up being something that's several hundred, well, not several hundred feet long, but up to 100 feet long before it's cut to length. Now, we'll talk when we get to our discussion about columns. We'll talk about residual stresses that are imposed in these members. The steel doesn't cool uniformly. The tips of the flanges and the center of the web cool more quickly than the rest of the cross section, so that actually imposes some residual stresses in the cross section. And those residual stresses can cause the members to warp or with some initial camber or initial sweep, maybe even some twisting in them. So they have to be straightened before they can be shipped. So then the final operation is to actually straighten the members to within ASTM tolerances, and that's usually done using a rotary straightener like the one that's shown here. All right, so that brings us to the end of this lecture. Hopefully by now you understand that steel is produced in a three-step process where pig iron is made out of raw materials. Then pig iron is combined with alloying elements to form steel, and then that steel is formed into the structural shapes that we use, like I-beams or channels and angles or plates and things of that nature. So understanding how steel is produced is important to understand how we design it, how to predict what its strength is. And as we move through the rest of the semester, we'll come back and talk about the production methods that were described herein so that we can better understand how to account for the inherent characteristics that were imposed in the steel. Okay, thanks.